I was a physics grad student in the late 70s at Cornell, which for those of you that don't know is a somewhat isolated place. I recall rather vividly having a very simplified view of the intellectual geography of our field. There was the East Coast of the United States. Cornell was kind of tenuously connected to that. There was the Midwest, well, not very much of it, but a little bit. And then there was the fabled charms of the West Coast. And then there was Europe, and then there was Israel. And I didn't really think about that very much. You know, what the remarkable nature of that map really was, that a country with, I guess, about a sixth of the population of California loomed so large. And, well, as I've grown older and I've done my own bits of group building and group maintenance, I've come to really appreciate what a remarkable thing Israeli physics represents. And at least in our field, the people we're honoring, there they are, you know, have played a really major role in building and maintaining that. And I really admire greatly what you've done. And maybe more honestly, I have to say that I envy, you know, the skill and the subtlety and the diplomacy that you've brought to this task. And that envy is very sincere. All right. I've never actually written a paper with either Eliezer or Shimon, and of course it's not too late for that. But in a very genuine way, we have collaborated. We've worked on many of the same things, and we reflected on the same questions. And certainly, my own work has been influenced a lot by the papers that I've read of both of you. And in fact, one of the sort of key tests for myself of the validity of ideas I'm working on is whether Shimon and Eliezer have worked on these ideas. And I'm afraid that does bring me to a rather awkward point. What I'm going to talk about, eternal inflation, what I have been thinking about it recently, as far as I can tell, appears nowhere in the collected papers of Shimon or Eliezer. So I guess it's not too late for them or for me to correct this situation. And so I'd like you to, both of you, to regard this talk as a kind of invitation. Or again, maybe more honestly, a cry for help in thinking about these ideas. Okay, so inflation. Now, all of you know basically what this is. It's certainly one of the most remarkable phenomena in the physics of gravity. You all know the basic setup. You start in some metastable state, and then you have a scale factor that increases exponentially with time in this enormous explosion that inflation represents. Of course, this doesn't go on forever. This metastable state can decay. Typically, we call this some kind of instanton tunneling, Coleman-DeLucia tunneling in this context. And in most regimes, this dimensionless tunneling rate called epsilon is e to the minus some action and is much less than 1. And in a causal Penrose diagram, this would be de Sitter space. This would be a bubble nucleated by this instanton. Now, as Nadi mentioned, in flat space, in condensed matter physics, this kind of instability is very well known. You can have supercooled water, and eventually you tunnel and form a droplet, and your whole system turns to ice. In gravity, there's a profound distance. While the system is trying to tunnel and turn into ice, the system itself is exponentially expanding. So you have a race. Okay? The system is exponentially expanding, and droplets are trying to kick you out of the unstable state. And because this tunneling rate can be small, typically tunneling loses this race. And in fact, you find the space growing bigger and bigger, the system trying to make droplets of the stable phase, but losing. And you form this picture of successive diamonds. But they never really fill up space. In fact, an exponentially large amount of space is left inflating. We call that eternal inflation, I guess, for obvious reasons. Okay. And it's the signal on this kind of causal diagram is you have a bunch of diamonds, smaller and smaller. They eventually form a fractal. The amount of space that's not in the diamond forms a measure zero fractal, often called the inflationary fractal. So that's, in a nutshell, one part of the phenomenon of eternal inflation that we want to talk about. Well, it's a fascinating phenomenon. I hope you'll agree. But there are a lot of fascinating phenomena in the world. And so the question is, why should we waste our time thinking about it? And I think The answer for me, at least, was the advent of our understanding of the landscape. That string theory most likely contains a very large number of metastable, isolated states, as well as stable states. Here's a baby picture of a landscape. You have some metastable states, some stable states. And then, in the cosmology of such a system, you start from, let's say, this highest metastable state. You form this kind of multicolored picture of eternal inflation. You have lots of bubbles of different types. You might call this the multiverse. Okay? And it raises a new and rich question. Very roughly, how many bubbles of each type are there? And this question is ill-posed, and a lot of what we'll do is to try to make it more well-posed. And the payoff would be not just having another fascinating phenomenon, but having some kind of selection mechanism telling us which of these kinds of vacua are more likely in some vague and unspecified sense. And that would be a good thing. I guess it would be a good thing. In fancier words, our goal will be to develop a measure for eternal inflation. Now, I guess the first thing that comes to mind, and came to mind with early workers in the field, is you might just say, well, pick the volume of each bubble. The stuff with the biggest volume wins. Well, I have to say that I am attracted to that idea, but it is very problematic in a lot of ways, and so we'll put it aside. There's another interesting suggestion by these people, Garriga, Schwartz-Parloff, Malenkin, and Winitsky, of a year or two ago, that motivated a lot of this work. And so let me talk about it a bit. Their idea basically is to count bubbles, not count the volume, but just count the types of bubbles, and then do a little post-processing afterwards that we won't talk about. Now, of course, if you wait for an infinite time, there's an infinite number of bubbles. So you have to regulate it somehow. And their proposal was to cut this process off in co-moving time. Why co-moving? Well, we'll give some kind of justification for that in a little while. So again, if you have a metric of this form, you talk about co-moving coordinates t and x, the spatial coordinates. Well, in co-moving coordinates, t and x, these 45-degree bubbles that I drew turn into tongues. And the later a bubble forms, the narrower the tongue. So you have a picture like this. Now, if you imagine slicing this picture at a fixed co-moving time, this is a 3-space and 1-time setup, so you would get a 3-dimensional space, drawn for obvious reasons as 2-dimensional here. And you would have the sphere of the green type vacuum, the screen of the, I guess, orange vacuum, and within it, some brown spheres. This eventually, as you go larger and larger time, you have smaller and smaller bubbles. It forms a fractal. Again, another presentation of this inflationary fractal. And their idea is basically, at a given time, take the ratio of different kinds of bubbles, and that defines a measure, the probability of having a certain kind of bubble. Now, you can see here that the largest number of bubbles, the largest probability of a type, comes from, let's say, these brown guys, the progeny of a long-lived bubble. The progeny dominate if the bubble is long-lived, because if it takes a long time to nucleate these, they'll be very tiny tongues, and so you'll fill up with a lot of them. So remember the slogan, that this measure favors the progeny of long-lived bubbles. Offspring. Okay. Well, this is a nice idea. It has actually a lot of nice properties that I should have mentioned earlier. It turns out it's independent on the detailed way that you define co-moving coordinates. It's independent of the way you start the system off. It agrees with a couple of cases that are simple enough we think we know the answer. And so it's a nice reference measure and has been thought about a lot. One thing it is, though, is a global measure. You're comparing things all the way across this huge inflating space-time. In particular, you have to count up information from regions that are spatially disconnected and will never come into causal contact. Experience, and experience especially of this community, indicates caution in doing this. Okay. Thinking about black holes, concepts like holography and black hole complementarity tell you, be careful. Okay? You can easily overcount. If you apply global techniques to, for instance, thinking about black holes, you predict things like that black holes should lose information. So be cautious. Again, this doesn't mean that these global pictures, these pretty diagrams like this, are without meaning. It just means the meaning might be more subtle and there might be redundancies in the meaning. The safest course, if you're counting, would be, we think, to focus on what a single observer can see. Okay? Because there are going to be redundancies in what a single observer can see. So this leads us to think about single observer measures on eternal inflation. The first proposal here was made by Busso. It's a very simple proposal and a good one, which is just to monitor the local environment an observer sees. I start in this vacuum. I count every now and then. I tunnel into another vacuum. I start in vacuum A. I tunnel into vacuum B. Let's assume that you can survive these tunneling processes. This is theoretical physics. You tunnel into vacuum C. Maybe you bounce back up to vacuum B. You can do that. And then maybe you hit a terminal vacuum T. In this kind of string, vacuum B would be, by his measure, would be favored twice as much as the others. More technically, he counts the number of times you enter a particular type of vacuum. Okay, and it just means the observer is sensitive to his local surroundings. But a single observer can see more than this. And so part of what I want to talk about is exploring the consequences of this extra information that a single observer can acquire. This is work that I've done with Alex Maloney, Lenny Susskind, who's a very promising young physicist at Stanford, and myself. I guess I should retract the word young, but promising certainly. So the idea is consider an observer of a special kind ending in a stable, supersymmetric, zero cosmological constant vacuum. Such a stable thing allows you to discuss asymptotic ideas. Here we're drawing on ideas by Van Freevogel, Sakino, Susskind, and Ye. And so this would be such a tunneling from a de Sitter space into that zero cosmological constant terminal vacuum. In this context, we call this such a thing a hat. And here's the observer going into the hat. And for measurement purposes, let's refer to this observer as the Censustaker. We'll take a census of what kind of bubbles he can see. And a key point is that the Censustaker can see many bubbles. And this goes back to the early work of Guth and Eric Weinberg, and is emphasized in its role in this process by these authors, that you don't have an isolated final hat bubble. There are collisions of all different kinds of bubbles with this final hat. In the simplest case, the collisions might look something like this. And it's not just two. You can have an infinite number of collisions, and the bubble looks more like a lizard with little scales on its skin. And the Censustaker can look back in his past light cone and see all of these colliding bubbles. So instead of talking about a single final bubble, we can talk about an infinite collision cluster. And there's a lot of information about the kinds of bubbles in the system in that collision cluster. And I guess I should emphasize before I go on, I guess I'll get to it in a minute. So let's present this a little bit more explicitly. So here's, this didn't really come out too well. Here's the Censustaker. This is this final hat. Let's describe this bubbles by looking at an initial surface at constant, let's say, FRW time for this bubble. That's this constant negative curvature disk drawn in this lime green here. And these bubbles that make a collision represent these kind of geodesics you find in constant negative curvature spaces that you're probably familiar with. And then you ask, at a certain time, this Censustaker looks back along his light cones, and what does he see? Well, here's the intersection of his light cone with this FRW surface, and he sees these pieces of these tracks of these bubble walls. So the sky now would be a two-dimensional sky. The census taker would see bubbles of different sizes corresponding how much of an intersection this light cone has with these various bubbles. And as you go later and later in time, the light cones encompass more and more of these bubble collisions, and you see a growing set of such bubbles. The bubbles that intersect later make smaller domain walls on the surface, and so represent smaller spots on the sky. And so the pattern is very similar to this co-moving time setup that later corresponds to smaller, except here, co-moving time, a somewhat arbitrary notion, is replaced by a manifestly physical time, the time of this census-taking observer. And it's not surprising, given this picture, that if we ask the census taker to count bubbles, in simple landscapes, you actually find that the census taker measure of counting bubbles, a manifestly physical single observer measure, corresponds with this global co-moving time measure. This will not be the case, as I'll mention in a minute, in more complicated landscapes. Before I go on then, there's a point I think that transcends the details of what I'm talking about, and I learned from Lenny and his collaborators, that a single observer sees an effective multiverse. This is what a single observer can see, and it has all the complications of this multiverse that we talked about. So a multiverse by itself is not a global notion. A good single observer description is going to have to include this full complexity of lots and lots of different kinds of bubbles. Yes. It is, but it doesn't matter. The word sky. You're not supposed to read the words, okay?
See, what's simple and what's complicated?
Well, sorry. A simple situation would be if there were not an infinitely large number of bubbles of all different sizes. Okay? You might have thought that this pattern of lots and lots of different bubbles was a phenomenon of thinking globally. Okay, you'd have all these different bubbles. And I think I might have thought that. But the point is that because of bubble collisions, of this collision cluster, it's not something that you only see in a global way of thinking. You can see an infinite number of bubbles. A single observer can see that. And so even in a single observer... Oh, I'm sorry. Yeah, I will come to that in just a second. Okay. Yeah. Yes.
Can I just ask a
Yes.
question about the observer?
Yes.
So if I understand correctly what's going on,
Yeah.
even though these constant time surfaces are homogeneous,
Yes.
you're picking a specific observer that comes in at the bottom of that light cone and just follows the...
Yeah, there's a lot of subtleties there, but let's say for now...
People who are off axis.
That's right, and you might ask how much it depends, and there's some recent interesting work about that it's more dependent than I at least might have thought. There's worth of Guth and collaborators. I think the statement is, in certain situations at least, the fine-scale nature of this fractal is independent of the choice of observer. So the measure will be. There might be a large-scale dipole moment that will depend. But the fine-scale nature of the fractal won't be. Francois, go ahead.
Why can't the internal time in these things that you take
Yes.
there, from time reversal, why can't they go the opposite way?
There's an initial condition you apply that you start in a highly excited, inflated state. I mean, it's like cosmology. You know, you start with something special.
Roughly on all of that. Apparently there's no reason why you can't get things going both ways in time.
Well, you can formally draw a de Sitter space that goes both ways. That's true.
Yeah, so these things they have to go.
Well, another thing that's once you end up in one of these terminals, you don't ever hop back. So there's an asymmetry that way too. There's an issue of terminals, but I guess maybe that's a better answer of what's asymmetric. Okay, so now I need to come back to David's question. Oh, I'm sorry.
In our history, how many did we meet?
Now that's an awkward question that I'm going to come to. Not too many. Okay. Okay, but we've only lived a tiny, tiny time. Okay. Okay, so now I have to go back and address this question So I asserted in certain simple landscapes, this bubble counting is the same. In more complicated landscapes, and what I mean here, there are many factors that can drive this not to be true. I think the most significant is that not all bubbles of very different kinds of vacua form nice domain walls, nice stable domain walls with the Censustaker bubble. And if you don't form a good domain wall, you won't be able to see it on the sky in this way. You could imagine that there's only an inflating domain wall, so the bubble never really gets to hit the Censustaker. You can imagine it forms a crunch all the time. So there's a detailed question of the nature of the landscape, and it's not just counting isolated bubbles, but how they interact with each other. And in a complicated landscape, it seems pretty likely you're not going to be able to make nice domain walls with a given Censustaker bubble. So this means that the Censustaker measure will depend on the final hat, on where the observer ends. It always has the same qualitative property as this Garriga et al. Measure in that it favors the progeny, the available progeny of long-lived vacua, the offspring. So we could go back and agonize about how we're supposed to interpret this, and we probably should at some point. But for now, let me agonize about another issue, which is common to all of these final hats and to this global measure of Garriga et al. The probabilities that you compute depend on the lifetimes. Remember, what's favored are the progeny of long-lived bubbles. And depending on lifetimes are exponentially sensitive to the basic parameters of the vacuum. For instance, SUSY breaking, if the scale of the gravitino mass was m3/2, very simple models might give a lifetime that goes like x of some mass scale over m3/2 squared. Noddy presented some models that had another kind of exponential dependence. But it's characteristic that you should have an exponential dependence on the amount of supersymmetry breaking. And so long-lived vacua can be found easily by having very low amounts of supersymmetry breaking. Now, we're not sure what those vacua would decay into, what their progeny are, but they might well decay into vacua with even lower amounts of supersymmetry breaking. And so it seems that, not unlikely, that such a measure is going to favor exponentially very low supersymmetry breaking scales. That's certainly not required, and we can imagine situations where it's not, but I think you might imagine finding some like that.
Steve?
Yeah.
Why does it need to be supersymmetries are local now?
Well, that could be the case as well. That would be, yes, that's certainly a possibility as well.
In fact, according to you, that's where you end up getting.
Well,
That's the most likely one.
yeah, that's right. It could well be that if people sometimes put another cut of a anthropic nature that you don't want to be an absolutely zero supersymmetry. But you're right. If you just counting bubbles, that would be like. Right. Okay. So that's where I think you're going to be. So my question, which is not well written on the bottom of the slide, is why is SUSY breaking in our world so high? Okay. Why do we have to build the LHC? Why can't I make super partners in my TV set? Okay. Milli-electron belt will be even easier, right? But, okay. And this seems to be a serious problem. And I'm sorry? The only problem? Right. Well, and there are one can construct other related problems that these measures have this exponential push to very long-lived, and so they can get you, because of this exponential push, into very weird places. And they don't seem to conform to things that we see. So,
these weird places tunnel to other weird places, to generic?
well, it's hard, for instance, suppose you have very low supersymmetry breaking. It's kind of hard to tunnel to very high supersymmetry breaking. It could tunnel to zero.
I disagree with that.
Why? Completely or just sometimes?
Completely.
Really? Okay.
If you have a small cosmological constant,
Yes.
your low supersymmetry, small positive one,
Right.
okay, you're going to decay into a negative CC big crunch, which is not supersymmetric at all. Okay? The fact that that place on the potential also supports a supersymmetric ABS vacuum, fine.
No. I'm sorry. I want to put an anthropic cut in there. Whatever, you throw away the things you decay into that are not anthropically acceptable. You're certainly right. The most likely thing you'll decay into are crunches. Okay, but what things can you decay into that are not, that are, let's say, have an entropic possibility?
Well, if you're talking about a long-lived, almost supersymmetric vacuum,
Yes.
it will always decay into a crunch.
No, there might be a rare possibility to decay into something else.
No, anytime the cosmological constant is negative, it's a crunch.
No, suppose there's a positive cosmological constant, almost supersymmetric vacuum.
Yes.
It could decay into something with a smaller positive cosmological constant and a lower supersymmetry breaking.
Oh, I see.
All right, so
So those are the only ones you accept
because of an anthropic, I'm putting an anthropic cut, okay? Now, I think, if you had a measure that was not so strongly pushed, you would safely, I would be happy to ignore that possibility. But this measure has such a strong push that my feeling is that those are going to really be serious. And I guess I view this, although there's certainly not a no-go theorem because we don't understand enough about the landscape and what can decay into each other. It's very worrisome for this kind of measure. And by worrisome, I mean it would give some pattern that would roughly correspond to what you can see in the world. So what's wrong? Okay. Well, one possibility is that there's some exotic features of the landscape that I have not understood that make such a strong push fit with what we see in the world. Well, I guess there's an initial possibility that this whole setup is misguided. That was for you, David. Okay. All right. Then there's but then there are other possibilities. It's certainly, I don't think we wants to discard this whole setup because of that. There are other possibilities that this measure is just not the right thing to determine, the conditions that we're living in now. Perhaps we're asking the wrong question. Maybe we don't just want to count bubbles. We want to add some other feature, the volumes of bubbles or something. I must say there's nothing obvious to me that would make this work. One could go further out on a limb and say that perhaps this disinterested census taker living out in this flat bubble is not sufficiently involved in this process. Perhaps we need to require that the census taker must live where he works. Okay. That would be that since you might regard observers to have to locally see around them the environment that you want to count. So you might, as a very arbitrary rule, just say that the probability is proportional to the number of bubbles of type A that an observer living in an A bubble can see. I'm not pretending to motivate that well. But then there is a dynamical effect that if the cosmological constant in the A bubble is positive, as ours is, there's a de Sitter horizon of order 1 over Hubble of A that puts a maximum distance out which you can see. Now, you might say it's pretty large, it's 10 to the 10th light years or whatever. But, and this is a dynamical issue in the things we know about the landscape, that lifetimes are exponential in parameters, and so typically are much greater than the time and length scales of de Sitter horizons. So typically, even in a bubble of our kind, this goes back to your question, Eliezer, the horizon of 10 to the 10th light years, we probably won't have seen any bubbles interacting with us. So in this case, this measure of seeing all these bubbles in the sky becomes kind of vacuous, and you're reduced back to this original idea of Busso's, that all you should do is look in your local environment and see what's there. I don't know if that's true, but one thing it does is it reduces this exponential pressure that is so worrisome. So maybe we should talk a bit more about this Busso measure, which basically says, look around you and count the number of times, assuming you can survive these transitions, you enter in a certain kind of vacuum. This measure depends on initial conditions. It's not too hard to see. But it does, in an interesting way, have a substantial selection power. And recently, Busso and his student Yang studied this measure on a simple model landscape, the Busso-Polchinski flux landscape. And I'll just tell you the kind of results they found, because they might illustrate, if you had a better understanding of this idea, is what you might find. Yeah?
What kind of signal did you expect to see in the sky? I mean, it depends. The spectrum of radiation associated with the de Sitter doesn't obscure any signal, every signal, unless you assume that everything.
Well, there's a horizon problem. There's a causality problem of looking at light.
Right.
I mean, just light rays don't make contact. So I was thinking about electromagnetic radiation.
Oh, you're just using a causal.
Yeah, just a causal. I mean, it's really, I mean, these bubbles hit very late. And the tunneling probabilities could be e to the 10 to the 40th seconds. And that's way outside the 10 to the 10th light years. Okay. So again, to remind you, a simple model of a landscape is to have fluxes around cycles. Here's 2 cycles. You'd need maybe several hundred of these. It turns out, by analyzing things, this Busso measure favors the diagonals on this lattice. It doesn't like a lot of flux in cycle 2 versus none in cycle 1. And suppose you pick some anthropic shell with a small cc that has 10 to the 80th vacuum in it. This was just with some...
How do you have to know something about the dynamics?
That's right. So in these simple flux vacua, you assume that you have the tunneling of D-brane pair creation. You have a specific, you can calculate the Coleman-DeLucia tunneling amplitudes. It's D-brane creation. And the formulas are known. So you assume that those tunneling processes, you assume those rates. So that's the model. It's this configuration and D-brane nucleation to take you between them. And so you set up a set of parameters. So the anthropic shell has maybe 10 to the 80th vacuum in it. That's enough, for instance, to explain anthropically the value of the CC. And then you ask for Busso measure things that are favored by, I don't know, 1 part in 10 to the 6th. And the number of selected vacuums in the anthropic shell compared to the total is a factor of like 10 to the minus 41. So there's still about 10 to the, 39 vacua that are selected by the measure, but that's many fewer than just this flat measure would predict. And there's some discernible patterns, this pattern of not liking random fluxes, but liking fluxes on the diagonals. So this is, well, this is an interesting, as a kind of model of what you might hope for. Yes? Did somebody have a question? Yes.
What is the error of this number 10 to the 8?
Let me pass on that. Let me pass on that, Barak. Yeah.
How can you calculate this measure, which requires knowing the dynamics of the transitions between the various vacuums, without knowing the value of the cosmological constant as a function of the dynamic?
You do. In this model, you have a formula for it. This is a very oversimplified model. But it's a model.
Well, it's a model of a formula. I mean, you don't really have a calculation.
In this model, you do have a formula. I mean, it's a.
Why have a model if you need a formula?
Yeah.
You need to assume the bare value.
The formula comes from some motivated thing involving wrapped D-branes, and you assume that the energy is proportional to the flux. The free parameters are the sizes of the various cycles. And so there is a. Well, that's right. Roughly speaking, it's the size of the cycles and the flux numbers.
So Steve,
Yeah.
in a more realistic model, the cosmological constant would have a kind of random value over a lattice like that?
I'm not sure it'd be random. Probably more flux will generally make higher.
All the radiative corrections from the different particle species which have to be.
All of those things would have to be there, yeah. So it would be certainly very complicated.
So the idea that you're tunneling from one nearest neighbor to another is probably not correct.
Well, I mean, the dominant transitions might well be from brain nucleation in certain parts, so that I would think that there's transitions that are easier than others. So I don't think it would be completely random, although but the structure would be more complicated for sure.
I think what Michael is asking is what the radiative corrections move those points around so much that you can't really answer.
Especially if you already you require a cancellation of more than 10. To get to that 10 to the 80, you have to have this incredible cancellation.
Right.
So the simple estimate of just fluxing, balancing,
I think the
is
point
going to
is
be
not,
washed out.
Yeah,
the point is
right.
not that this model is right in detail. The point is more, suppose you've done this model to this kind of selection, then you would proceed. Maybe this is encouraging to do better.
I think that, you're right. Thank you. I think that's a good way of saying it. But I think it's an interesting, although maybe very difficult thing to do, to think or to try to guesstimate what this kind of measure would predict in a more realistic kind of model, the kind that Michael Douglas has worked on. This involves, as a big new step, understanding not just the locations of these vacua, but the transitions between them. And that's not, it doesn't seem impossibly difficult to try to understand. And so,
you have an additional complication with the negative cosmological constant vacua appearing. In this case, you don't have...
No. Here that you do have negative cosmological constant. The entropic circle is out here someplace. Yeah, so that's built into this. Right? But the point I want to draw attention to is that even with this rather mild selection process, without this kind of multiversal thing, there is significant preference for one kind of vacuum over another. Okay? And so this might be, well, the fantasy would be, suppose there's a distinctive pattern that this measure predicts. And then you might, if you could confirm this pattern in a more realistic thing, that might give you a guess. If you found things in the real world that were not inconsistent with that pattern, that might give you some comfort. I'm sure if they were not consistent, you would find some reason to not to worry about it. But that would be the hope. All right, well, your questions have made clear that this comment is in order. It's a clear and unfinished story. I guess I would like to say, though, that it's an important story, because if we have this plethora of vacuums, if we want to say something about selection, this is an important part of what that might entail. Now, small parts of this story can be made more precise. And so let me now, in the last part of my talk, turn to some of those parts. So one kind of vacuum that I haven't talked about directly, although the questions have, is what happens if you have a negative cosmological constant, like this minima here. So if you imagine falling in here, the scale factor tends to 0. And generically, what happens is you have a crunch. You have a singularity at some finite time. So if this is the bubble tunneling into a nice flat vacuum, this is what happens if a bubble of negative cosmological constant forms. You have some kind of singularity. This is, of course, very qualitative. And the question is, what is the nature of these crunching bubbles? What role do they play? How do they appear to the census taker? Would be maybe a concrete question. So Ben Friedvogel, Gary Horowitz, and I looked at this. We wrote a paper recently called Colliding with the Crunching Bubble. So let's maybe first remind you about some basic notions here. Suppose you have this very simple situation of a negative CC A vacuum and a 0 CC B vacuum. Now, in flat space, B would always be unstable. But that's not the case when you include gravity, because this lambda, this cosmological constant less than 0 vacuum creates an anti-de Sitter space. And an anti-de Sitter space, the volume of a space is proportional to its area. So therefore, the tension of the domain wall connecting these two vacuums can balance this volume energy that in flat space would always win. All right. At this balance portion, if A and B happen to be supersymmetric, this tension has a BPS value. There's a BPS domain wall. And this BPS value is the smallest tension you can have for which B is still a stable vacuum. Now, the domain wall could have higher tension, but supersymmetry requires that the tension be at least the BPS value. Otherwise, this vacuum would be unstable. Well, so I'll just say a few words about the technology we used to try to address this. It's essentially a problem building GR solutions in these cases. If these are the space-time cones for these nucleating bubbles, such two bubbles intersect in hyperbolas. So it's natural to use hyperbolic slicing. You would write a metric in the Schwarzschild-like form, but instead of having a sphere here, you have a hyperbolic 2 geometry. And then further, let's use thin wall approximation. These domain walls are thinner than the characteristic scales of the curvature lengths. So then you come up with 3 cases which we can analyze, we think, reliably. In the first case, this tension is less than the ADS scale. It's less than the BPS bound. This is not allowed by Susan. In this case, this flat bubble would be unstable to nucleation. what happens is this collision hits this flat bubble, and it kind of triggers the instability. It's like dropping a seed into supercooled water. It causes this flat bubble to crunch. And so the Censustaker bubble just crunches, and the Censustaker has a very rough time with it. By assuming supersymmetry, we can assume that that case does not occur. The second case is when the tension is greater than the ADS scale, greater than the BPS bound. Then the domain wall, in some sense, is very heavy, and not very much of it wants to be around. And so the domain wall is expelled from the Censustaker bubble. Here's the nucleated Censustaker bubble. Here's the nucleated negative CC bubble. They hit, form a domain wall, which actually accelerates out. It's not clear in this Penrose diagram, but it hits this null infinity, which means it's being accelerated out. And it essentially never really enters the Censustaker bubble at all. The future null and time-like infinity of the Censustaker bubble is essentially unchanged. It's sort of a minor nuisance here. The third case, sort of the most interesting and subtle case, is when the tension is equal to the ADS scale. It's a BPS case. In this case, again, roughly speaking, there's no force on the domain wall because the volume energy balances the wall tension. And so the domain wall moves like a free massive particle toward future time-like infinity. Here's the 0 CC bubble. Here's the negative CC bubble. Here's the domain wall moving toward future time-like infinity. And then what happens is the negative CC bubble crunches, but the Censustaker sees that singularity cloaked behind the horizon of a hyperbolic anti-de Sitter black hole. It turns out, and I certainly didn't know this, that you can have black holes that have standard spherical horizons. You can also have them with hyperbolic horizons. And that's what the Censustaker sees. It never evaporates. Not only is it an ADS black hole, but it's got an infinite hyperbolic horizon, which suppresses various kinds of recurrences. And it remains a permanent black blot on the sky that the Censustaker sees. Further, let me point out that, remember you had this nice hat, this nice green diamond in the absence of this collision. This crunch has taken up a finite fraction of that hat. Here as it's drawn, it's roughly half. If you have a later collision, it might, as these later collisions do, take up a smaller amount, a quarter. And you have this fractal slicing of this hat. And so in a very strange way, a finite piece of future infinity is removed in the first collision. Repeated collisions shred the future infinity into a fractal, leaving only a set of measure 0 untouched. So this most stable place for a Censustaker to live, this nice 0 cosmological constant, supersymmetric vacuum, is not as stable as we might have thought. What we really want for the Censustaker is to live in a crunch-proof hat. And the question I'll leave you with is, where in the landscape can we find such things? Well, thank you.
Relative to this last comment, it would be perfectly consistent with our world if we lived in a crunchy hat that's eventually
As long as the lifetime is long, we could live in really a completely unstable world. As long as the lifetime was, long enough.
If I understood Tom's comment, it's more likely that we live in a place where there's, asymptotically as we go into the future, constant flipping out of crunches that take pieces out of the crunch.
That's right. And that's certainly, well, that's certainly
if that were
likely.
actually true, it would destroy this Busso measure. Because the Busso measure.
No, the Busso measure, sort of this chain in the Busso measure ends in whatever terminal you're in. That terminal could be a crunch. Okay, but then you could count the steps on the way to that terminal. There would still be a well-defined process of computation. Busso's measure does not require this nice census taker that I was talking about.
I said the wrong thing. It annihilates the census taker measure. The census taker's measure says
That without putting some kind of cut to prevent that. That's right. Yes.
Okay, so let me try to annihilate the Busso rule of measuring.
Good.
Now, the whole idea, as I understand it, is to say in a single causal patch,
Right.
You don't overcount, and you avoid all of the puzzles and confusions of behind the horizon and so forth. But if you do that, you should count everything in the causal patch.
Right.
Not just what you decide you want to calculate,
Right.
but you want to count, you want to count everything.
Right.
In particular, why don't you count the horizon, which is part of what's inside the causal patch?
Right. It would have to be some coarse-grained phenomenology. I don't know of any principled reason.
Would that destroy the results?
Probably. Yeah, I haven't thought about it hard. I think, well, we've had this discussion a little bit before. My guess is it would be pretty dangerous. I mean, it would depend on what you do with the horizon entropy. This spot counting or this local environment is a kind of special processing of that. So I think you could certainly by that process, you could invent back the census taker measure, as you know very well. So you could push it probably to any answer you wanted.
Or you could even reinvent the lengthening measure.
That's almost certainly the case. Yeah. So.
Are you saying we should wait the vacuum by the horizon entropy?
Well, no, that would be the most simple. You wouldn't know. The point is that there's an enormous amount of information.
I'm sorry, Steve. Could you just define the term because I don't understand what it means? Count the horizon entropy.
Well, in a bubble of let's see.
Yeah.
So in some de Sitter space, you just imagine an observer moving in some de Sitter space. You can find some kind of static patch that represents the horizon. And within that horizon, reliable but not completely rigorous estimates indicate that there is an entropy available to you. That would be the entropy you'd compute by taking the horizon size and dividing by the area in Planck units, computing the size of the horizon. That presumably represents real degrees of freedom. Most of that looks to us like sort of Hawking radiation kind of stuff, and it looks essentially random. Yet subtly hidden in that Hawking radiation is probably a lot of order that tells you about the way the patch was made or about subtle things that might be eventually going to hit this bubble or things like that. And if you process it enough, you might be able to extract.
There's no way for a local observer to extract all the information in the horizon.
That's fair. I think that's fair. But so
local observer can extract about part of the 3 halves.
That's a good point. Yeah. All right. Yeah. That's you're right. All right. So that's a point. Although I'm worried that it's still possible if you process that hard enough to get into trouble.
So I'm sorry. So what is a local observer going to do with this entropy in order to create a measure of vacuum?
Well, the simplest thing would be to ignore it. That was the implicit. That was Busso's proposal.
What did Lenny want to do?
What did you want to do, Lenny? You wanted to.
Well, I'm just saying, if the logic is that you shouldn't overcount,
Yes.
you still should count everything within the causal patch.
So Lenny, you want to weight the vacuum by the horizon?
No. Busso wants to weight the states by their entropy, by the amount of increase of entropy of a certain.
Well, that's a second level of processing that I didn't mention here. That's you're right, of course, but that's it after this effect.
Yeah, that's it.
It's after this counting effect. Yes.
Right. But then you're supposed to measure, you're supposed to weigh vacuums. If you want to take what you calculated,
Right.
very, very much depended on throwing away parts of the entropy.
Absolutely. That's correct.
Right. The question is, what's the good logic of that? The entropy that's...
What is the definition of the Busso measure?
Well, there's two pieces to it, but the simplest piece that I presented is you sort of take one bit from, you enter some kind of de Sitter space, and you look around, and you measure the standard model parameters. So there's 17, I don't know, a small number of bits. But then there's a second level of post-processing you could apply that I didn't discuss, where you might weight the vacuum by, I don't know, the amount of entropy increase in the process.
That's where prediction comes from. That's where the calculation comes from.
Yes, but that he would, in hindsight, he would try to pull that. And there are many more things available to you. I guess you're right, it's not the full entropy, but there still is a lot of bits that you can measure. And the question is, do you want to take that very long bit string and do some very exotic arithmetic operation to it? And there's absolutely, I don't know of any principled reason to reject that. I mean, at this stage, as you can see, and well, as we've talked together, I think in some sense the only way to proceed is almost phenomenologically, and to see what looks like a sensible answer. Yeah.
If I can leave this with some question. I was really intrigued by your last question and the statement you made just before it. It seems to me you were saying that this idea that these locally supersymmetric bubbles are kind of stable places with asymptotia is just wrong. And how do you propose that we'll avoid that?
Well, I think
because there are always negative CC bubbles in the landscape.
Well, I think it's possible. I mean, I think you've thought about this more than me, that you could find negative CC bubbles, but the domain wall is greater than the BPS tension. That's all. You can certainly have, it seems in simple models, you can find a supersymmetric minimum connected to negative CC things, but the domain wall tension is greater than the BPS bound.
Yeah, sure.
Okay, so if it's greater than the BPS bound, you don't destroy the hat. It's only if the domain wall is at the BPS bound.
Oh.
Okay, and so I think you'd be happy to find examples.
No, but that's very unlikely. Right.
The what's unlikely?
That it's exactly.
Well, I think I can talk myself into thinking a D braid might well be at the BPS bound. And so if you make flux transitions, if you have a lot of places to go, and one of them.
Yeah, but it's very unlikely that both of these vacuum states are both supersymmetric.
Well, but there might be. All you need is one of them to transition to. You have a lot of places to go. If you have one BPS thing, then you're in trouble. So I'm not sure of the estimate, but well, yes, not. Does that mean that you want to withdraw your question? Or?
Outside of question. I know what the answer to that is. If you're not from Palo Alto, you get hit by a negative.
I don't understand.
I hate it when you say that, but all right. Go ahead. Okay, so that in a very meager way, that was what the Censustaker idea could answer. You look up in the sky, you count spots. That's an operational thing. And you count the spots at 10 million years, you write them in your book, and you take ratios. At 20 million years, you take ratios. And in certain model systems, at least, you limit.
Probability to see a particular spot.
That's right.
It's not a statement about, it's not a probability of being in a particular vacuum.
Well, that's right. And that may well be the, exactly. And so at the,
What does it mean to be probability 10 to the minus 40 in a particular vacuum?
well, there's a mathematical procedure that Busso suggested. What it means, so there's a well-defined algorithm. You start at a given vacuum and you hop according to rules. You use the instanton transition rules, and you generate a set of chains.
You don't survive these hops. No, not just because of the domain wall. Standard model is different here.
Yeah, okay. So you're invoking an anthropic problem.
No, I'm not.
No, but...
I don't understand if you start playing this game.
Yeah.
It seems to me that the co-moving time that you take is to start with just a kinematical significance. Therefore, I don't see why the internal time that would develop within any of these bubbles should be correlated to that time. It could go not only forward or backwards, it could go in any sense.
Well,
I don't understand exactly why you organize the whole thing with respect to a single time defined by a kinematical object.
So you're talking about the global measure.
The global measure. It seems to me that you can involve all kinds of time going in, and then I don't see what you're going to do.
Thank you, Francois. I appreciate that question. I agree with you wholeheartedly. And that was one of the motivations of looking to see what a single observer sees. The time a single observer keeps track of is sensible. And in simple cases, that correlates exactly with co-moving time. Basically, because the scale factor at the edge of this FRW patch locks in the scale factor of these bubbles that hit it. So in those cases, co-moving time, which I agree is somewhat arbitrary, has a good observational operational significance. And then, so the idea would be not to do that, okay? And that would be the advantage of these single observer measures. And so this looking on the sky is a well-defined measure. It just doesn't seem to answer the question we're interested in, and that's a shame. And, yes.
Yeah, one more question about this supersymmetric progeny disaster.
Okay, good. Yeah, if you can get out of it, that would be delightful.
Suppose the counting that is currently being done is wrong in the exponent by factors of 5.
What the counting in the landscape?
Suppose we're living in the lowest possible value of the positive cosmological constant that there is, or the most supersymmetric universe that there can possibly be that's not exactly supersymmetric.
That might be fine. That well.
So then your measure would give you exactly what you want.
I'll buy you a bottle of whatever you want to drink.
Do that in advance of it being proven.
Let me clarify what I mean to say. Well, right, there could be oddities about the landscape that makes this generic worry not a worry. I think some of the ideas you've had about these other I can't remember what you call them. These other kinds of very stable de Sitter spaces, great divide. You can imagine that monkeying with that would make supersymmetry not the major drive to a long lifetime. And maybe, so if you accept non-genericities in this landscape, then the objection becomes less severe. But that opens its own can of worms.
But it could just be the question of the 10 to the 500 being wrong, and it's really 10 to the 100 or 10 to the 80 or whatever the number is.
But then I guess you have to ask why we happen to, why that happens to coincide with this particular number. Why isn't it 100, 10 to the 6 times larger than the value we see? It would take some kind of miracle to line up with the value that we see. No, but why if it's right at the bottom, why were there any vacuums that were anthropically acceptable? That would be a miracle. Why in the deep wheels and gears of nature was one vacuum right?
These landscape guys are going to calculate this and, have a great theory of the universe.
It actually sounds sort of like intelligent design.
On that note.
We should have another question. That's really not the right one.